PostgreSQL powers Instagram, Uber, Netflix, and Spotify. It handles trillions of queries every single day across some of the most demanding applications on the planet. And between 2023 and 2025, it received 3 major releases, versions 16, 17, and 18, each packed with game-changing features that fundamentally improved how it performs and what it can do. From asynchronous I/O that delivers 3x performance gains to native vector search for AI applications, PostgreSQL has evolved far beyond what most people think of as a simple relational database. This is the complete deep dive into PostgreSQL, its architecture, its killer features, and everything new in the latest releases. Whether you're evaluating databases for a new project or looking to level up your existing PostgreSQL knowledge, this video covers it all. Let's start with what PostgreSQL actually is and why it matters so much in 2025 and beyond. PostgreSQL, often called simply Postgres, is an open-source, object-relational database management system. It originated as a research project called Postgres at the University of California, Berkeley in 1986, led by Professor Michael Stonebreaker. That means it has nearly 40 years of active development behind it, decades of battle testing in production environments, decades of bug fixes, performance tuning, and feature additions driven by real-world needs. No other open-source database comes close to this track record. It's widely considered the most advanced open-source database system in the world, and it has earned that title through consistent, disciplined engineering over 4 decades. Let's break down the core properties that make PostgreSQL what it is and why enterprises trust it with their most critical data. First, it's fully ACID compliant. That stands for atomicity, consistency, isolation, and durability. Atomicity means every transaction either completes fully or rolls back completely. There's no partial state where half your writes succeed and half fail. Consistency means the database always moves from one valid state to another, never violating your constraints or integrity rules. Isolation means concurrent transactions don't interfere with each other. Each transaction sees a consistent view of the data. And durability means once a transaction is committed, it stays committed even if the server crashes 1 millisecond later, even if the power fails, even if the disk controller resets. These guarantees are non-negotiable for financial transactions, user data, medical records, and anything where data integrity matters. Second, PostgreSQL is incredibly extensible. You can create custom data types, custom functions in multiple programming languages, PL/pgSQL, Python, Perl, even C, custom operators, custom aggregate functions, and even custom index access methods. This extensibility is why the ecosystem of PostgreSQL extensions is so rich and powerful. Third, it follows the SQL standard more closely than virtually any other database. When the SQL standard defines how something should work, PostgreSQL implements it correctly. But it also extends beyond the standard with powerful features that other databases have been catching up to for years. So why do companies choose PostgreSQL over MySQL, SQL Server, or other databases? Let me give you the concrete reasons. JSON and JSONB support lets you store semi-structured document data directly in Postgres. JSONB in particular gives you binary stored JSON with full indexing capabilities. You can use GIN indexes to query nested fields at incredible speed. For most applications that need some document storage alongside relational data, you genuinely don't need MongoDB. You get the flexibility of documents with the reliability of a relational database, full ACID transactions, and critically, the ability to join document data with your relational tables in a single query. Common Table Expressions, or CTEs, let you write complex queries as readable, named building blocks. Recursive CTEs can traverse trees, process graphs, and handle hierarchical data that would require multiple queries in other databases. Window functions give you analytical superpowers, running totals, moving averages, rankings, percentiles, lead and lag operations, all calculated efficiently in a single pass over the data. Lateral joins let you reference earlier tables inside subqueries in the from clause, enabling query patterns that are literally impossible in standard SQL. The extension ecosystem multiplies PostgreSQL's capabilities exponentially. PostGIS adds complete geospatial support, coordinate systems, geometry types, spatial indexing, distance calculations, and area computations. It's the gold standard for geographic information systems. TimescaleDB transforms PostgreSQL into a time series powerhouse with automatic partitioning and specialized aggregation. And pgvector adds AI-powered vector similarity search, something we'll explore in depth later in this video. The companies using PostgreSQL span every industry and every scale. Instagram uses it as their primary data store, handling billions of photos and social interactions with PostgreSQL's JSONB and custom sharding layer. Uber relies on it for trip data, driver information, and real-time dispatch, one of the most demanding workloads in tech. Spotify stores user profiles, playlists, and listening history in PostgreSQL, running thousands of instances globally. Apple runs it across multiple internal services and iCloud infrastructure. Reddit's billions of posts, comments, and upvotes live in PostgreSQL. Twitch processes real-time, streaming metadata with it. The UK's National Health Service trusts it with sensitive patient records. Financial institutions run trading platforms on it. Government agencies store citizen data in it. Even companies that initially chose other databases, MySQL, DynamoDB, Cassandra, frequently migrate to PostgreSQL as their needs mature because it handles complexity, correctness, and mixed workloads better than specialized alternatives. Now let's dive into the architecture. This is where PostgreSQL truly differentiates itself from other databases, and understanding the architecture is essential for running it effectively in production. PostgreSQL uses a process-based architecture. This is fundamentally different from MySQL's thread-based model. When a client connects to PostgreSQL, the postmaster process, which is the main PostgreSQL daemon that listens for incoming connections, forks a brand new backend process to handle that specific connection. That backend process is responsible for parsing queries, creating execution plans, executing those plans, and returning results for that single client connection. Each backend process has its own private memory space. This provides incredibly strong isolation between connections. If one query runs out of memory or hits a bug, it doesn't crash other connections. The process simply dies, and the postmaster spawns a new one. This architectural decision prioritizes stability and reliability over raw connection throughput. The trade-off is that each process consumes more memory than a thread would, typically 5 to 10 megabytes per idle connection. This is why connection pooling is absolutely essential in production. At the center of PostgreSQL's memory architecture are shared buffers. This is a region of shared memory that all backend processes can access simultaneously. It serves as a cache for data pages, the 8 kilobyte blocks that PostgreSQL uses to store table and index data on disk. When a query needs to read data, the backend first checks shared buffers. If the page is already cached, called a buffer hit, the read is extremely fast, just a memory access. If the page isn't cached, a buffer miss, PostgreSQL must read it from disk, which is orders of magnitude slower. In production environments with dedicated database servers, you typically set shared buffers to about 25% of total available RAM. Setting it higher isn't always better because the operating system also caches file data, and you want to leave room for that double caching effect. Write-ahead logging, commonly called WAL, is PostgreSQL's mechanism for guaranteeing durability and enabling crash recovery. The principle is simple but powerful. Before any change is written to the actual data files on disk, that change is first recorded in the WAL, a sequential log of all modifications. If the server crashes, PostgreSQL can replay the WAL entries to recover any committed transactions that hadn't been flushed to the data files yet. This means you never lose committed data, even on an unexpected power failure. WAL serves a dual purpose. Beyond crash recovery, it's also the foundation for all forms of replication. Streaming replication works by continuously shipping WAL records from the primary server to standby servers, which replay them to stay synchronized. Logical replication decodes WAL records into logical change events that subscribers can consume. Point-in-time recovery uses archived WAL segments to restore a database to any moment in the past. WAL is truly the backbone of PostgreSQL's reliability and high availability story. Multi-version concurrency control, or MVCC, is how PostgreSQL handles the fundamental challenge of concurrent access, multiple users reading and writing simultaneously without corrupting data or blocking each other. Unlike databases that use exclusive locks on rows or pages, PostgreSQL keeps multiple versions of each row in the table. Here's how it works. When you update a row, PostgreSQL doesn't modify the existing row in place. Instead, it marks the old version as dead, no longer visible to new transactions, and inserts a completely new version of the row with the updated values. Readers see a consistent snapshot of the data based on when their transaction started. They never see half-updated rows. And critically, readers never block writers, and writers never block readers. This makes PostgreSQL exceptionally good at read-heavy workloads where many users query data simultaneously while updates are happening. The downside of MVCC is that dead tuples, those old row versions, accumulate over time. If you have a table with 1 million rows and you update every row once, you now have 2 million row versions stored on disk, even though only 1 million are actually visible. This is where Vacuum comes in. The Vacuum process is PostgreSQL's garbage collector. It scans tables, identifies dead tuples that are no longer visible to any active transaction, and marks that space as available for reuse. Without regular vacuuming, your tables grow forever, a phenomenon called table bloat, and query performance degrades as the database scans through millions of invisible dead rows. Auto-vacuum is the built-in daemon that runs vacuum automatically based on configurable thresholds. Tuning auto-vacuum properly, how aggressively it runs, how much I/O it's allowed to consume, and how frequently it triggers, is one of the most critical aspects of PostgreSQL administration. Many production performance crises trace directly back to auto-vacuum falling behind on busy tables. For storage, PostgreSQL uses heap tables. Data is stored in 8 kilobyte pages, and new rows are inserted into whatever page has sufficient free space, tracked by the free space map. This means rows aren't stored in any particular order by default, unlike clustered indexes in SQL Server. Sequential scans read pages in physical order. For values that exceed about 2 kilobytes, PostgreSQL uses Toast, the oversized attribute storage technique. Toast automatically compresses large values, and, if they're still too big, stores them in a separate Toast table. This happens transparently. Your queries work the same way regardless of whether values are Toast or not. It's an elegant solution that keeps the main table's pages efficiently packed while still supporting arbitrarily large values. Connection pooling deserves special emphasis because it's the single most common source of problems for PostgreSQL newcomers. Because each connection spawns a separate operating system process, having thousands of connections open, even idle ones, consumes significant memory and system resources. Most applications don't actually need thousands of simultaneous database connections. They need thousands of application connections, but only a fraction of those are executing queries at any given moment. pgbouncer is the most widely deployed connection pooler. It sits between your application and PostgreSQL, accepts thousands of client connections, and multiplexes them across a much smaller pool of actual PostgreSQL connections. In transaction pooling mode, a PostgreSQL connection is assigned to a client only for the duration of a transaction, then returned to the pool for another client to use. This can reduce your actual PostgreSQL process count from thousands down to 20 or 30. Piccat is a newer Rust-based alternative that adds load balancing across multiple PostgreSQL instances and built-in query routing. For any production deployment expecting more than 50 to 100 concurrent connections, a pooler is not optional. It's mandatory. Now let's talk about PostgreSQL's killer features, the capabilities that make developers choose it over all alternatives. JSONB support effectively turns PostgreSQL into a document database. You can store arbitrary JSON documents in a JSONB column, create GIN indexes on the content, and query nested fields using operators like the arrow operator for accessing keys and the double arrow operator for extracting text values. You can test for key existence, search within arrays, and update nested values, all with full ACID transactional guarantees. For the vast majority of applications that want some flexible, schema-less storage, JSONB eliminates the need for a separate MongoDB deployment. You get documents and relations in one database, queryable together. Full-text search is built directly into PostgreSQL with no extensions needed. You create vector columns that store pre-processed, stemmed text. You create query objects that represent search conditions. GIN indexes make searches fast, even on millions of documents. PostgreSQL handles stemming, reducing words to their root form, stop word removal, language-specific rules, and ranking by relevance. For standard search, finding articles, products, or documentation, PostgreSQL's built-in search eliminates the operational overhead of maintaining a separate Elasticsearch cluster. It's not as feature-rich for complex scoring or faceted navigation, but for 80% of search needs, it's more than sufficient. The extension ecosystem is what makes PostgreSQL uniquely powerful. PostGIS doesn't just add a geometry type, it provides a complete geospatial computing platform. Spatial reference systems, coordinate transformations, topology operations, raster data processing, and spatial indexing using R trees and GIST indexes. If you're building anything with maps, locations, or geographic data, PostGIS is the industry standard. pgvector brings vector similarity search to PostgreSQL, enabling AI and machine learning applications without separate infrastructure. We'll cover this in detail in its own section. TimescaleDB extends PostgreSQL for time series workloads with automatic partitioning by time intervals, compression of older data, continuous aggregates that pre-compute summaries, and retention policies that automatically delete old data. It turns PostgreSQL into a genuine alternative to InfluxDB or Prometheus for metrics and telemetry storage. Table partitioning lets you divide massive tables into smaller physical pieces while maintaining a single logical table interface. Range partitioning splits data by value ranges, most commonly dates. List partitioning separates data by discrete categories. Hash partitioning distributes data evenly across a fixed number of partitions. The query planner automatically eliminates irrelevant partitions, called partition pruning, so queries only scan the data they actually need. A table with 5 billion rows partitioned by month means a query for January's data only reads 1/12 of the total. Logical replication provides fine-grained, table-level replication between PostgreSQL instances. Unlike streaming replication, which copies everything, logical replication lets you replicate specific tables to specific destinations. You can replicate between different PostgreSQL major versions, useful during upgrades. You can replicate to multiple subscribers with different table subsets. You can transform data during replication. This flexibility makes logical replication the tool of choice for data distribution, incremental migration, and real-time data integration scenarios. Row-level security, or RLS, is PostgreSQL's mechanism for defining access policies at the row level. You create policies that specify which rows a given user or role can see, insert, update, or delete. For multi-tenant SaaS applications, this is transformative. Instead of filtering by tenant ID in every single query across your entire application code, you define the policy once at the database level, and it's enforced automatically for all queries. A developer accidentally writing a query without the tenant filter can't leak data because the database won't return rows outside their tenant. This defense-in-depth approach catches bugs that application-level filtering alone would miss. Now let's cover what's new in the recent major releases. PostgreSQL 16 was released in September 2023, PostgreSQL 17 in September 2024, and PostgreSQL 18 in September 2025. Together, these three releases represent a massive leap forward. PostgreSQL 16 brought several groundbreaking improvements. Logical replication from standby servers was a game-changer for high-availability architectures. Previously, logical replication subscribers had to connect to the primary server, adding load to your most critical instance. Now subscribers can connect to hot standby replicas instead, completely offloading replication traffic from the primary. This enables change data capture workflows and data integration pipelines without impacting your primary's performance. Query parallelism expanded significantly in PostgreSQL 16. Full and right outer hash joins can now run in parallel, as can the string_ag and array_ag aggregate functions. Incremental sorts gain support for select distinct queries. These improvements collectively mean more of your complex queries automatically leverage multiple CPU cores. The new pg_stat_io view was a major observability win. It exposes detailed I/O statistics, reads, writes, extends, hits, evictions, and FSYNCS, broken down by backend type, context, and object type. For the first time, DBAs have clear visibility into exactly what's generating I/O load and where cache misses are occurring. This replaces educated guessing with concrete data for I/O tuning. Bulk loading performance improved substantially in PostgreSQL 16 through better buffer management during copy operations. Large data imports, the kind you do during ETL processes or initial database loads, became measurably faster. Access control gained regular expression matching in pg_hp, NF, allowing pattern-based rules that dramatically simplify configuration for environments with many databases or dynamically named users. PostgreSQL 17, released in September 2024, continued the momentum with even more impactful features. The headline edition was comprehensive SQL/JSON support. The JSON_table function converts JSON data directly into a standard relational table representation that you can query with regular SQL. This eliminates the need for complex JSON extraction and unnesting patterns that were previously required. JSON_query extracts portions of a JSON document. JSON constructors build JSON values from SQL expressions. These additions bring PostgreSQL to near-complete SQL/JSON standard compliance. Incremental backup support landed in PostgreSQL 17, fundamentally changing backup strategy for large databases. Previously, every backup was a full copy of all data files, which for terabyte-scale databases could take hours and consume enormous storage. Incremental backups capture only the WL and data changes since the last backup, reducing both backup duration and storage requirements by an order of magnitude for active databases. The Vacuum system received a complete memory management overhaul in PostgreSQL 17. Previous versions could consume excessive memory when vacuuming tables with many dead tuples. The new implementation uses bounded memory regardless of table size, making vacuum behavior predictable and preventing out-of-memory conditions during maintenance operations. Write throughput under high concurrency improved through optimizations to WL insertion locking, reducing contention when many connections commit simultaneously. The merge command, which performs insert, update, or delete conditionally in a single statement, gained returning clause support and additional condition flexibility. Logical replication slots are now preserved during major version upgrades via pg_upgrade, eliminating the painful need to rebuild replication configurations after upgrading. But the most transformative release was PostgreSQL 18, shipped in September 2025, with over 3,000 commits introducing fundamental architectural changes. The asynchronous I/O subsystem is the biggest architectural change in PostgreSQL in over a decade. For its entire history, PostgreSQL used synchronous I/O. When a backend process needed data from disk, it issued a read system call and blocked, waiting idle until the operating system completed the disk read. On a single spinning disk, this was fine. But on modern NVMe SSDs capable of hundreds of thousands of I/O operations per second, blocking on each one individually leaves massive performance on the table. The new async I/O subsystem allows PostgreSQL to issue multiple I/O requests simultaneously using operating system primitives like IO_uring on Linux. The database can prefetch upcoming pages while processing current ones, keeping the CPU and storage device busy in parallel. The PostgreSQL team demonstrated up to 3x performance improvements for sequential scans and significant gains for bitmap heap scans, vacuum operations, and bulk reads. This single feature brings PostgreSQL's I/O performance dramatically closer to purpose-built analytical engines. Skip scan for multi-column B-tree indexes addresses a long-standing limitation. Previously, a composite index on columns A and B was essentially useless for queries filtering only on column B. The database couldn't efficiently use the index without a condition on the leading column. Skip scan changes this by jumping over distinct values of column A, effectively using the index for column B queries alone. This makes composite indexes far more versatile and reduces the need for separate single-column indexes. Virtual generated columns store no data on disk. Their values are computed dynamically from other columns whenever the row is read.